All right, welcome to Notes 2-2, Day 2. We are on page 24. We're going to start off with cube roots now. So cube roots are related to square roots, right? It's the same principle. The difference is instead of looking for perfect squares, we're looking for perfect cubes. And so it says the process of finding roots can be expanded to cube roots. Finding the root of a number or an expression is the inverse operation of cubing that number. So for example, the cube root, there's my index, of 125 equals 5, because 5 times 5 times 5 is 125. So meaning if I have the cube root of 5 to the third power, which that's 5 times 5 times 5, the cube root and the cube will reduce and I'll be left with 5. Similarly, the cube root and the cube reduce and I'm left with y under the radical. Okay, so we're going to go ahead and list off perfect cubes. So the first perfect cube would be 1 cubed. 1 cubed is 1. So off to the side, 1 cubed is 1. 2 cubed is 2 times 2 times 2, which is 8. 3 cubed is 27. 4 cubed, 16 times 4 is 64. 5 cubed is 125. 6 cubed is 216. And 7 cubed is 343. All right, I would expect you to know at least through 7, but you should also know 8 cubed. So on your calculator, we're going to do 8 times 8 times 8, which is 512. So 8 cubed is 512. 9 cubed, again on my calculator, 9 cubed is 729, and 10 cubed is 1000. All right, so these perfect cubes, we're going to need to be able to recognize these perfect cubes. So we're going to simplify these perfect cubes in the same way that we simplified our perfect squares. So for A, I have the cube root of 16. Now, 16 was not one of my perfect cubes, so I'm going to have to break 16 into some numbers that I know, like 8 times 2. What I notice is that 8 is a perfect cube, and so I know that this is 2 cubed, right, is 8, and then times the cube root of 2. The cube root and the cube reduce each other. They're inverses, so that I'm left with 2. And this would be a non-perfect cube, so it'll stay cube root 2. Now you notice that my index should be tucked in my radical. It's tucked inside, right here, inside the radical. So please make sure that you do the same. All right, so this would be 2 cube root 2, as they said. Let's do the next one. Example B. B says 3 cube root of 128. Now I notice that 128 is not on my list of perfect cubes. 128 is not a perfect cube, so I need to find two numbers that will multiply to 128. So 128 is 64 times 2. So I'm going to rewrite this as the cube root. Oh, don't forget your 3 outside, right? The cube root of 64 times 2, which is 3. Cube root of 64 is a perfect cube. It's 4 cubed. And then cube root 2. Again, the cube and the cube root are inverses, so we're left with 3. There's multiplication happening here, so that's times 4, and then cube root of 2. 3 times 4 is 12, and then we cannot evaluate the cube root of 2. So indeed we have 3 times 4 times cube root 2, which is 12 cube root 2. And finally, try the C. C is the cube root of x to the 5th. So I can rewrite this as one of two ways. I can either rewrite it as x to the third times x to the second. Now the reason I want x to the third is because I'm looking for perfect cubes, which would be the cube root of x cubed times the cube root of x squared. And cubes and cube roots reduce, so I have x and then cube root x squared. Or the other method I can use would be to expand this out. This is the cube root of x to the fifth. So I have 5 x's. I'm looking for groups of 3. So I'll take out this group of 3. It comes out as an x. And under the radical, I have x to the second left. Whichever method you prefer, you may use. Oh, I cut that off. I'm going to go through it one more time. I expanded this out as x times x times x times x times x. That's x to the fifth. I'm looking for groups of 3. I have a group of 3 that's going to come out as a perfect cube, which is x. And under the radical, I have x squared left. All right, at this point, you should pause the video and do the try these. So please pause your video, try these, and then come back to check your answers. All right, the cube root of 24. The cube root of 24 is not one of my perfect cubes. So I'm going to find a perfect cube that goes into 24 like 8. 8 times 3 is 24. I can rewrite that as the cube root of 8 times the cube root of 3. The cube root of 8 is 2. And the cube root of 3 cannot be simplified. All right, the next one, 54. 54 is not one of my perfect cubes. However, I see 27 times 2 will give me 54, so I'm going to rewrite this one as the cube root of 27 times 2. And I'll split my variable. This is the cube root of z to the third. Now I know that cubes and cube roots are inverses, so I'm left with a z. And the cube root of 27, I'll rewrite that separately from the cube root of 2. The cube root of 27 is 3. This z is going to come out front with it, and the cube root of 2 is going to stick by itself, right? It cannot be evaluated. Another way to do this problem would be to expand this out. So you've got 27, which is 3 times 3 times 3 times 2, and then times z times z times z, and then triples will come out. So groups of 3 come out, that's a 3. Another group of 3, we have z's. A z comes out, and under the radical is a 2. Do not forget it's a cube root. You can use either method that you prefer. If you like expanding these out, you can do that. I'm going to repeat that method right here. So I'll repeat that idea with 8 and 3. This is 8 is 2 times 2 times 2, and then times 3 for our to make 24. Here's a perfect cube. It's going to come out 2, and under the radical, we're going to have a root 3, cube root 3. All right, the last one, 40. I notice 40 is not a perfect cube. In fact, I don't think that there is a perfect cube in 40 other than 8. So we're going to rewrite this as the cube root of 8 times 5, and then the cube root of b times b times b times b. There's b to the 4th power. Remember, I'm looking for groups of 3, so this set of 3 is going to come out. I'll have a b outside. The cube root of 8. The cube root of 8 is 2. And under the radical, I have a 5 and a b, so I'll have cube root 5b. If you want to see the fully expanded method, we could do that as well. We could go cube root 8 is 2 times 2 times 2 times 5. That's 40. And then b times b times b times b. And again, we're looking for triples. So that 2 is going to come out. This set of b's is going to come out. And under the radical, we would have cube root 5 and b. All right, let's go on to page 25, the check your understanding. So you should, again, pause here, try the check your understanding, See if you get them correct. It says a kite has a base with a dimension of 2 by 3 feet. 2 by 3. What is the length of one crossbar needed to stabilize the kite? So this is going to be a 2 by 3. So we have 2 squared plus 3 squared equals, I'm looking for my hypotenuse, c squared. That would be 4 plus 9 equals c squared. Again, we're on number 4. That would be 13 equals c squared. So c would be the square root of 13. Square root 13. All right, let's go ahead and simplify. Number 5. We're going to simplify. I'm going to do these on a separate piece of paper. So to simplify, number 5a, square root of 124. Again, I'm looking for perfect squares. If you don't know what number goes into 124, you can always start prime factoring it. So 2 times 62 is 124. I still don't see any pairs or perfect squares. So that would be 2 times, we could rewrite that as 2 times 31 is 62. At this point, I see this is a perfect square, so it will come outside. I have 2, and then 31 is a prime number. It is done. 2 root 31. Let's try B. The square root of 125 d to the 4th. I'm going to write this as, I'm going to prime factor it. So I've got 5 times 5 times 5 is 125. D to the 4th is d times d times d times d. And I am looking for pairs. So I have a pair of 5s that comes out. All right, this is the square root of 25, which is 5. I have a pair of d's that will come out. That's a d. I have another pair of d's that will come out. That's another d. And under the radical is only the 5. And then I can rewrite this as 5. D times d is d to the 2nd. And then square root 5. C. C is the cube root of 250. Now I see right away that this could be rewritten as 125 times 2, and that 125 was one of my perfect squares. 125, right, is 5, I'm sorry, perfect cubes is 5 times 5 times 5. Or, right, so you could just write this as this is 5, and then under the radical is the 2. Or you could prime factor this, 5 times 5 times 5 times 2. Don't forget your index. And then we're looking for perfect cubes or triples, so that's going to come outside, and under the radical will be a 2. And finally on D, we have cube root 81 m to the 7th. I'm going to prime factor that. This would be 81 is 9 times 9, and then m times m times m times m times m times m times m. That's 7 times. I'm going to rewrite this again. That's 3 times 3 times 3 times 3, right? 3 times 3 is 9, 3 times 3 is 9. And then 7 m's. I hope at this point you're starting to see some patterns happening, right? If you can picture how many sets of 3 you can take out of a set of 7, I know I can take out 2 sets of 3, and I'll have 1 left over. So I know an M will come out and another M will come out. So I'll have an M and an M. And here I will have a group of 3. So a 3 will come out. Under the radical, under my radical, I'll have a 3 and an M. And then I can rewrite this as 3m to the 2nd, cube root 3m. All right, moving along. Another way to write a radical expression is with a fractional exponent. So a fractional exponent says make use of structure. Use the definition of a radical and the properties of exponents to simplify the expressions of each row in the table. The first row has been done for you. All right, so you may wonder where this 1/2 came from because they just spring that on us. So in a square root, right, our index is a 2. And the number under the radicand could be any number, but the exponent on it is generally a 1. So if I were to rewrite this, I could rewrite this as a to the 1/2 power. Right, my exponent and my index. So I'm going to label that. This is always the exponent, and this is always the index. So for example, if I had the square root of 7, I could rewrite this. Whoops, I'm sorry. I was off to the side there. I'll say that again. So this is the square root of, my index is a 2. We don't generally write it. I could have any number under the radical, right? This is my radicand. My exponent here would be a 1. And so I could rewrite that as a to the 1/2 power. Always the top number is your exponent, and the bottom number, the denominator, is the index. So I could rewrite square root of 7 as 7. My exponent is 1. My index is 2. This is the same as 7 to the 1/2 power. All right, so they said that the square root of 16 is 4. The square root of 16 is 4. 4 times 4 is 16. We can also rewrite this as 16 to the 1/2 times 16 to the 1/2. If we're multiplying the same base, we would add these exponents. 1/2 plus 1/2 is 1, and 16 to the first is 16. We're going to apply that same idea here. The cube root of 3 is 2, the cube root of 8 is 2. The cube root of 8 is 2. The cube root of 8 is 2. 2 times 2 times 2 is 8. This could be rewritten as 8 to the 1/3, 8 to the 1/3, 8 to the 1/3, which would be 8 to the 1/3 plus 1/3 plus 1/3, which would be 8 to the 3/3, or 8 to the first power, and 8 to the first power is 1. So they are showing you why you can rewrite this index 1/3 using this notation. So the same thing here, the 4th root of 81. So now we're looking for something that when we do multiply it 4 times is 81. 81 is equal to 3 times 3 times 3 times 3. 3 times 3 is 9 times 3, 3 times 3 is 9 times 3 is 27 times 3 is 81. So the 4th root, right, of 81 is 3 times 3 times 3 times 3, which is 81. We can rewrite this as 81 to the 4th, 81 to the 4th, 81 to the 4th, 81 to the 4th, which would be 81 to the 1/4 plus 1/4 plus 1/4 plus 1/4, which is 81 to the 4/4, or 81. All right, now we have to use the same idea here. The square root of a times the square root of a. Well, these are not perfect squares, so we could write that as the square root of a squared, which is equal to a, which would be a to the 1/2 times a to the 1/2, which would be a to the 1/2 plus 1/2, which is a to the 1/2 plus 1/2 is 1, or a. So it says, identify and describe any patterns in the table. Write a to the 1 over n as a radical expression. So now we have to be able to rewrite, right? We're going to have a radicand of a, an index. Our index is the denominator, and an exponent of 1. We don't really need to write that one, so this is the nth root of a. And they said that the general rule, so we are going to write this really big off to the side, the general rule. So this is any any rational exponent, right? A ratio or a fractional exponent can be rewritten as, that is my radicand, this is my index, which goes right here, and this is my exponent, which goes right here. And you can see that's what they've written. And then they say further, we could rewrite that as the nth root of a all to the m power. Those are equivalent. And it says the general rule for fractional exponents when the numerator is not a 1 is right here. All right, it says write 6 to the 2/3 as a radical expression. So I'm going to do that on a separate sheet of paper. So 6 to the 2/3, they show you two different methods. So I'm going to go through each. So for method 1, 6 to the 2/3 power, I'm going to apply that rule that I can write this as 6 to the 2 to the 1/3 power. Now, I'm allowed to do this. This is called the product or the power rule. If I multiply these two, right, 2 over 1 to 1/3, I'll have 2/3. So this is still 6 to the 2/3. 6 squared is 36 to the 1/3 power, which would be the cube root of 36. Or equivalently, they could have left it as 6 squared, which is what they did. Method number 2 is to say 6 to the 1/3 all to the second power. Remember, if I multiply my exponents, I still get 6 to the 2/3. 6 to the 1/3 to the second power can be rewritten as the cube root of 6 all squared, which is what they have written here. So here I should have left this as 6 squared, and I should have left this as 6 squared so that you could see that they are equivalent. Right? So the cube root of 6 squared is the same as the cube root of 6 all being squared. All right, the try these C, let's go ahead and try each of these. This is to write each as a radical expression. So we have 13 to the 1/4. 13 to the 1/4. Remember, this is my exponent. This is my index. So I'm going to rewrite this as 13 is my radicand. My index goes right here. It's a 4. My exponent is a 1. There's no need to write the 1. B, 7 to the 3/5 power. We're going to rewrite this. This is my index, and this is my exponent. So I'm going to have 7 cubed with the index of 5. So this is called the 5th root of 7 cubed. C, x to the 3/2. I'm going to rewrite that. Remember, this is my index. It's a 2. I really don't write a 2. If it's a square root, I leave it, it's implied that it's a 2. And this is my exponent. So my exponent is a 3. There, we've now rewritten each of these radical expressions. We're going to move on to page 26, the check your understanding. It says, what is the value of 6 to the 1/4 or 16 to the 1/4 power? So 16 to the 1/4 power can be rewritten as, this is the 4th root of 16. So we're looking for something that multiplies by itself 4 times and gives us 16. So I'm going to factor this. This is 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So therefore, the 4th root of 16 is 2. Next, we have 16 to the 3/4 power. I'm going to use the rule that we just saw a second ago which said that I can rewrite this as 16 to the 1/4 cubed. Those are equivalent. If I multiply my exponents, I will get 3/4. Now I'm going to do the same thing that I did just a second ago. I'm going to rewrite this as the 4th root of 16 cubed. The 4th root of 16 we just saw was 2. So this is going to be 2 to the 3rd power, and 2 cubed is 8. I'm going to do this a second way. 16 to the 3/4 power is equal to, I can rewrite this as the cube root of, the 4th root, there's my index, here's my exponent, 16 cubed. Now, if you want to cube 16 and then take the 4th root of it, you would need most likely a calculator to do that. 16 to the 3rd power is 4,096, and then you would take that to the 1/4 power. On your calculator, you would be raising that to the 1/4 power, and you're going to get 8. I prefer to take the root first, the 4th root of 16, so the 4th root of 16 cubed, which is 2 cubed, which is still 8. All right, it says for each radical expression, write an equivalent expression with a fractional exponent. All right, so my exponent is a 1, my index is a 2. This will be rewritten as, 15 to the exponent over index, 1/2. Here my exponent is a 1, my index is a 3, so this will be rewritten as 21 to the exponent over index. All right, guys, that was notes 2-2, day 2. I hope that you come prepared tomorrow with questions, and I will see you tomorrow.